Welcome back, everyone. We're going to talk today about chemical reactions, and in particular, talking about the equilibrium point of chemical reactions. So, a chemical reaction, you have reactants turning into products, and products turning into reactants in a sort of a back and forth kind of method. So, for instance, something like a reaction like water dissociating into hydrogen radicals and OH radicals in a process that goes back and forth. So you can have water splitting up into protons and OH radicals, or you can have the OH radicals and protons combining to form water. The reaction can go either way, depending on the circumstances, but for a given set of thermal conditions, pressure, temperature, etc., there will be some equilibrium point which is eventually met, and that's what we're going to talk about today. Where is the point in equilibrium, in chemical equilibrium? Where does this reaction stop? And we could parameterize that. We could think about that in terms of looking at the Gibbs free energy as a function of sort of how far has the reaction gone. We'd previously used the x the horizontal axis on our plots to represent, what's the ratio of this to that. Well, we could do that as what's the ratio of products, or what's the fraction of products versus reactants, so that if we have 0 over here, that means that we're in fact, in this case, in pure water, and if we had an x equals 1, then we would be completely disassociated. It is a little bit weird that we call this the reactant and this the product. We're thinking here about the reaction primarily going this direction. It's a little bit arbitrary. But in this case, basically, the reactants will be the things we put on the left of our chemical reactions, and the products will be the things that we put on the right of our chemical reactions. Now, since the Gibbs free energy of water is less than the Gibbs free energy of the radicals, then you might assume that the equilibrium point, it would be all the way over at the 0 end, that the reaction would just continue until we reached the point of pure water. But in fact, that's not actually what happens. There's always going to be a little bit of the radicals running around, because thermal collisions of the water molecules with one another as they collide into things. So here comes another water molecule, and they collide, smash, and off comes one of the protons, and you're left with an OH minus and an H plus drifting apart. And as they recoil off this reaction, they might bounce off in different directions, and there's going to be a lot of water molecules getting in their way, and it's the odds of every rogue proton finding a rogue OH radical to latch onto is kind of sort of, you can imagine that that's not really going to happen, that there's always going to be a few of these broken water molecules basically sitting in the bin. We can think about it also from the point of view of what we've been talking about in terms of Gibbs free energy. If we look here at the figure 5.41 from your text, what we can see here is that while yes, indeed, the Gibbs free energy for water is less than the Gibbs free energy for our products, our two radicals, once you start mixing the radicals in with the water molecules, then there is an entropy of mixing term, which we saw earlier has very, very sharp edges. The derivative of that entropy is infinite at the extremes, and so there will always be a little bit of a concave dip here, and by mixing your reactants and your products together, basically no chemical reaction will tend to go all the way to 0 or all the way to 1. There will always be some minimum equilibrium point a little bit separated from 0. Now, if this is a pretty steep function and the entropy of mixing is pretty weak, then this equilibrium point might be way, way, way down here. And if you're at the point where it's, you know, one atom and one molecule in a mole of stuff, then you can kind of say, yeah, that's pretty much gone all the way. But there will always be a little bit of possibility for materials of the other type, for the reaction to leave a little bit off of 0 or a little bit off of 1. And so that's sort of the premise that we're going to look at here. We're going to study how the chemical potential can be used to make predictions for sort of what the fraction of extent of our reaction goes. How far is it going to go to one end or another, and examine the nature of the chemical equilibrium that takes place. So let me just go back here to our page. If the point is to find where on this plot of Gibbs free energy versus the fraction of our material in, you know, reactants and the fraction of our material in products, then what we want to know is where is the local minimum of that Gibbs free energy term. That's going to be the EQ point, the equilibrium point. And that will occur at the place where all local minimums do when the slope of our Gibbs free energy curve is 0. Right? So that dg dx here is 0. And dx is basically a run of a single version of our reaction. That's the smallest unit of changing from products to reactants or reactants to products that our chemical system can undergo, is one exchange either to the left or to the right of our chemical reaction. Right, so a single exchange of the numbers on this side for numbers on that side, which means that what we're looking at is that the dg term, the change in our Gibbs free energy, then is going to be the 0, and that's going to be the sum of the changes of adding or subtracting single particles, right? So if we're going to take a water molecule and break it up into radicals, then we have to lose one water molecule and gain one each of those radicals, and we could write that as a sum over all of the products of the chemical potential of one of those products times the change in the number of those products. or the change in the number of those species. So this sum includes both the reactants and the products. You have to sum over all the, in this case, it would include a term for water, it will include a term for H+, it will include a term for OH-. Right? And in particular, for the water dissociation that we're talking about right here, if we're going to exchange one water molecule and break it up into one each of those products, then we're talking a DH2O, which is -1, and a DH+, which is +1, and a DOH+, or OH-, which is also +1. So in other words, we gain a H+, we gain an OH-, and we lose a water molecule. And under those conditions, this must be 0, so that if the dn over here, so we could write this sum out. Let's just go ahead and do that. We could say that 0 equals mu H2O, so the chemical potential of water, times -1, plus the chemical potential of the H+, times +1, plus the chemical potential of the OH-, times +1. Or in other words, that the chemical potential of water must equal the sum of the chemical potential of the H+ and the chemical potential of the OH-. Right, so that this then becomes our equilibrium condition. That the chemical potentials on either side of this equation must be in balance. And that sort of makes sense. That means that, remember, the chemical potential is the free energy essentially gained or lost by adding or subtracting a particular species of particle from our system. And if the Gibbs free energy lost by losing a water molecule is exactly balanced by the Gibbs free energy gained by gaining an H+ and an OH-, then yes, indeed, we're at a place where our Gibbs free energy has a 0 slope and therefore is at a local minimum. Technically, it could be a local maximum as well, but if you're looking for the equilibrium point, it must be at this place where this equilibrium condition is satisfied. Okay, so notice that this looks, if we compare that to our chemical equation, our chemical reaction, H+ plus OH-, notice that we have a term of the chemical potential at each location as we have one of our chemical species. So that this equation, our equilibrium condition, mirrors our chemical reaction. And we can see this in another example here that we're going to look at in today's lecture, which is the formation of ammonia. So in that case, we have nitrogen molecules plus hydrogen molecules turn into ammonia molecules. And if we look at, we have to, H2 and N2 come in diatomic molecules in a 3-to-1 ratio. So the smallest unit of reaction that will use up all of these reactants and form this product would be to do this reaction, or twice, in other words, well, that you have an N2 run into 3 different H2s to form 2 ammonia molecules. So in this case, DN2 will be -1 in one change of this reaction, and DH3 we're going to be -3. So we're going to lose 3, sorry, DH2, we're going to lose 3 H2 molecules, we're going to lose 1 N2 molecule, and we're going to gain 2 ammonia molecules. So again, the smallest change that this chemical reaction can make it includes those changes, and through the same method we saw down here, that's going to leave us with a chemical equilibrium equation that the chemical potential of nitrogen 2 plus 3 times the chemical potential of H2 is twice the chemical potential of ammonia. And again, our equilibrium equation, or our equilibrium condition, will be in the same form as our reaction with sort of the coefficients, the stoichiometric coefficients as they're known, out here in front, showing up in front of the chemical potentials as coefficients down here. And in the general case, if you have a chemical reaction that looks like some constant times species 1 plus some other constant times species 2, and so on and so forth, which can turn into some constant times species 3 plus some other constant times species 4, and so on and so on, then your chemical equilibrium condition will be that constant times the chemical potential of species 1, that constant nu times the chemical potential of x1 plus nu 2 times the chemical potential of x2, and so on, must equal nu 3 times the chemical potential of x3 plus nu 4 times the chemical potential of x4, and so on. So that again, the equilibrium equation, the equilibrium condition, will always mirror the chemical reaction. All right, so in order to see how to use this equilibrium condition, we're going to look at some example cases because the methodology for dealing with these chemical potential terms, right? Obviously what we have to do is, if we can evaluate these chemical potentials as functions of basically the concentration or amount of, or pressure, partial pressure of, or whatever it is that we're going to describe how much of each of these species we have, if we can come up with a form for the chemical potential in the various products and reactants as a function of their abundance, then it's just a matter of using those relationships for the chemical potentials and the equilibrium condition, and then solving for the ratio of abundances that would satisfy that equilibrium condition. But the way that we deal with the various chemical potentials depends on the form of the materials we're talking about. Is it a liquid? Is it a gas? Is it a solid? Are we talking about a solution and a solute, etc.? And the way we deal with these things varies a little bit from case to case. So we're going to do some example cases here and work through them. All right, well, let's go ahead and get along with our first example here. And so for our first example, we're going to use what's known as nitrogen fixation, which again is that formation of ammonia out of nitrogen, and hydrogen to form 2 ammonia molecules. And again, our equilibrium condition then is that the chemical potential of N2 plus 3 times the chemical potential of H2 must equal twice the chemical potential of ammonia. And in this case, we have 2 gases combining and turning into a gas. So we're in gas phase for all 3 species. And so we're just going to assume here the ideal gas law conditions. And in fact, go back to equation 5.40 in our text, which we looked at back in lecture 16, if you want to go back and look at it, for the chemical potential of a species in an ideal gas, which has the general form of the chemical potential at a given temperature and pressure is equal to the chemical potential at some fiducial temperature plus a term kT times the logarithm of the pressure that this reaction is taking place at divided by some fiducial pressure, typically something like 1 bar for our fiducial pressure. And so this P here represents the partial pressure of our species whose chemical potential we're trying to relate here. And so then if we use this form for our 3 chemical potentials here, then our equilibrium condition becomes mu naught N2 plus kT log of the partial pressure of N2 over our fiducial pressure plus 3 times mu naught for H2 plus 3 kT logarithm of the partial pressure of hydrogen with respect to our fiducial pressure. Must equal over here the chemical potential of ammonia, which is going to be twice the chemical potential of ammonia, so twice mu naught for NH3 plus kT logarithm of the pressure of the NH3, the ammonia, over our fiducial pressure. And again, typically our fiducial pressure is going to be something like 1 bar for whatever it is. Different tables will be tabulated slightly differently, but typically 1 atmosphere is a pretty common thing for the tables of these mu naughts to be written down in. So we're going to gather the kT logarithm terms on the left, the pressure terms on the left, and the sort of fiducial chemical potentials over on the right. So that's going to give us a thing that looks like kT times the logarithm of Pn2 over P naught plus 3 kT log of partial pressure of hydrogen over P naught minus 2 kT log of the partial pressure of ammonia over P naught. And that's going to be equal to twice the chemical potential for ammonia minus the chemical potential for nitrogen minus 3 times the chemical potential for hydrogen. And if we multiply everything through here by Avogadro's number, so multiply everything by Avogadro's number, then and combine these different logarithms. We're going to add those two, so that's going to multiply what's in the inside of those, and we're going to subtract this, so we're going to divide what's on the inside of that. Avogadro's number times K gives us the gas constant RT times the logarithm. We're going to have the N2 and the H2 on top, but the H2, there are 3 of those, so we're going to be cubing the H2. So N2 plus times PH2 cubed. And on the bottom we'll be left with the NH3. Again, the ammonia gets squared, P NH3 squared, and we'll have 2 P naughts left over on the bottom when we take the 4 on the top and the 2 on the bottom. That's going to leave us with an extra 2 here on the bottom. Left over, sorry, the 4 on the bottom from the top 2 terms, and the 2 on the top from the bottom 2 terms will give us 2 on the bottom there. And on the right, we're going to call that thing, which is Avogadro's number times this combination of chemical potentials, we're going to call that the change in the Gibbs free energy basically for the reaction itself. This term on the right becomes the standard Gibbs free energy for this reaction to take place for 1 mole of stuff being formed, and under the standard temperatures and pressures that these chemical potentials are tabulated and written down for. In other words, we're going to look up in tables what these chemical potentials are, and then we can make predictions for the behavior of this system at different partial pressures. So we'll look up the behaviors of pure ammonia, pure nitrogen, pure hydrogen, and then include these terms here. And we can rewrite things a little bit. We can bring the RT over. So logarithm of Pn2 PH2 cubed over P ammonia squared P naught squared equals delta G dot, or delta G naught over RT. And we could take the exponentiate both sides, Pn2 PH2 cubed over PNH3 squared. P naught squared is E to the delta G over RT. And typically the convention is to put this the other way round so that the products are on the top and the reactants are on the bottom. So we have to flip both sides of this. So that becomes then PNH3 squared P naught squared over PNH or PN2 squared PH2 cubed is E to the minus G delta G naught over RT, and we call that thing the equilibrium constant K, which is in principle a function of temperature, but not in fact in this case a function of the pressures, right? So there's an explicit temperature dependence here in the RT, but the pressure is being accounted for in this ratio over here. This is called the law of mass action in sort of chemical thermodynamics circles. And note that even if you don't have lookup tables, the fact that this isn't changing as a function of pressure tells you about the interrelationships of the partial pressures here of the products on the top and the reactants on the bottom. If you doubled the amount of reactants, for instance, that's going to give you, sorry, that's not squared. If you doubled the amount of reactants here, well, that's going to be twice N2, all right, so that's one factor of 2, and then twice H2 cubed, that's going to be 3 more factors of 2, so that's going to give us 4 factors of 2 on the bottom. And if this over here on the right is actually constant, then the only way this can be constant and this increased by a factor of 4 is if this also increases by a factor of 4. Sorry, 4 factors of 2, which is 16, then this here must also increase by 4 factors of 2 or 16, but it's only squared, which means that the partial pressure of ammonia would have to quadruple if you doubled the partial pressures of the reactants. So in other words, if you increase the pressure of the system in general, the reaction is going to drive the system towards ammonia and away from the reactants if you crank the pressure up. And that's because in this case, we go from 1, 2, 3, 4 molecules on the left to 1, 2 molecules on the right. So the 2 molecules on the right take up less space as a gas than the 4 molecules on the left. And so increasing the pressure of the system drives the equilibrium to the right towards the system that's going to take up less space. So it makes sense sort of intuitively. This is a version of Le Chatelier's principle, which is probably something you've run into in your introductory chemistry course, which says basically anytime you've got some sort of a chemical equilibrium and you push that system out of equilibrium, it will respond in such a way that it tries to counteract whatever the change was, right? So in this case, we had a system and we increased the pressure in that system, and the system responded by trying to decrease the pressure by going in the direction that took up less volume. It's kind of a bit like Lenz's law from electromagnetic induction, where the changing magnetic fields induces a current which generates a magnetic field in the opposite direction of the change. It's that sort of a thing. It's a negative feedback loop, basically. And Le Chatelier's principle, based on versions of this kind of thermodynamics, is an idea that equilibrium systems, when pushed out of equilibrium, will adjust to try and counteract whatever was pushing them out of equilibrium. If we wanted to calculate that constant K in this particular case, then we can go and look at our look in the back of our book, and if we zoom in and we look at the various reactants here, then NH3 here has a Gibbs free energy of minus 16.45 kilojoules. And so if we say that's per mole, right? So the Gibbs free energy of formation per mole of ammonia is minus 16.45 kilojoules per mole, and in this particular reaction, we're going to have if we basically multiply everything here by Avogadro's number, we're going to have 2 moles of ammonia being formed. So our delta G then for that 2 moles of ammonia at standard temperature and pressure would be minus 32.9 kilojoules. And so our constant K here is going to be e to the minus that, so e to the 32,900 joules divided by our gas constant 8.31 joules per Kelvin and our standard temperature 298 Kelvin, and that comes out to be about 5.9 times 10 to the 5, and armed with this value for our constant here, and if we took P naught here to be 1 bar, then we could, for a given, or we could calculate the partial pressures of ammonia, and given the partial pressures of the reactants, we could find the partial pressure of the product, or if we know the partial pressure we want of the product, we could find the partial pressures we need for the reactants and so on. So we would be able to determine how much of this stuff we would be able to, or we would need to generate or to run this reaction. All right. For our second reaction, we're going to look at the dissociation of water, which we also started off the lecture looking at. So our reaction here again is water H2O breaking up into hydrogen and OH radicals, leading to an equilibrium condition here that is the chemical potential of water is equal to the chemical potential of our H plus the chemical potential of our OH minus. And in the context of the dissociation, the natural or spontaneous dissociation of water into radicals, the equilibrium condition, spoilers, is that there aren't very many free radicals floating around in your glass of water. So this is going to be in the dilute solution limit, the one that we just looked at in the previous lecture, lecture 19. And indeed, if we then borrow the dilute solution chemical potentials for the solvent, that's equation 5.69, which is relevant to our solvent here being water, that the chemical potential of water is the fiducial chemical potential of water, what you would look up in a table, minus 2 terms for each of the solutes dissolved into our solvent. So the number of H plus divided by the number of H2Os times KT, and then minus another term here for the number of OH minuses divided by the number of water molecules, again times KT. And we're going to make the approximation here that, again, in the dilute limit, this ratio is going to be very small. The ratio of the radicals, number of radicals to the number of water molecules. And so the correction terms for water away from its sort of pure water chemical potential is so negligible as to be not really worth worrying about. All right, so in other words, basically, we're just going to assume that the radicals are such a small effect that it doesn't really affect the chemical potential of the water. For the solutes, in this case, our radicals, we use equation 570, again from a previous lecture, which had the form, the chemical potential of our H plus is going to be its fiducial chemical potential, again what you would look up in a table, plus this term Kt times the logarithm of the molality of the H plus. Again, that's the ratio of the number of moles of our solute divided by the number of kilograms of our solvent. And so you would look these up in a given table with molalities. Again, the chemical potential for OH will have the same form, some fiducial chemical potential for the OH molecule, plus a correction term for the molality of the OH. So in other words, these Kt log molality terms are corrections to the fiducial chemical potentials that take into account the densities, essentially, or the amount of reactants, or the amount of these solute molecules dissolved in our solvent, in our water. So again, we go back to the equilibrium condition, plug in these versions of things. So on the left, we're just left with the fiducial chemical potential of water. On the right, we have a mu naught H plus a Kt logarithm of the molality of H plus, plus a mu naught OH minus, plus a term Kt times the log of the molality of OH minus. And again, we're going to collect the log terms on the left and the chemical potential terms on the right, and that gives us something of the form Kt times the logarithm of MH plus times the logarithm, or times the molality of OH minus. So we took these two log terms, combined them by summing, and that means we multiply the things inside the logarithm. And that's got to equal on the other side. We're going to put the minus sign and put the mu H plus plus mu OH minus, these are all mu naught, H2O. And again, this is minus delta G naught on the left. And once we multiply again by Avogadro's number, and an RT log of the product of the molalities on the left equals minus delta G naught on the right. And just like we did before, we can divide by RT, unwind this logarithm, and we'll be left with, on the left, the product of the two molalities of our radicals, and on the right, e to the minus delta G naught over RT. So the exact same form of our equilibrium constant K, except that on the left here we have molalities instead of partial pressures as our way of tallying up the amount of these things. And the other thing to notice is that unlike the previous one, where it did depend on the pressures, or this constant was defined by the ratio of the pressures of both reactants and products, in this case, the water doesn't show up over here at all, which makes sense. First of all, we got rid of the water's dependence when we set those to 0, but the reason we get away with that is that the water, there's so much water that most of the water is just water. It doesn't really depend on how much water there is. All it really depends on is how much of these radicals there are, how much of the solutes. The solvent itself could be as large or as small as we want, because again, we're in the dilute limit, where the only thing that the solutes see is water, but the water sees itself mostly. So that's where we are with this dilute limit. Let's go ahead and take a look at this particular reaction. And if we go back to our table here, there is in fact a delta G of formation here for liquid water. There it is, minus 237 kilojoules. So the Gibbs free energy of formation for water in liquid form is minus 237.13 kilojoules. And if we look at what are we forming the water from, where the water is breaking up, into H plus radical in aqueous form. So that's a hydrogen molecule dissolved, or a hydrogen atom dissolved into the water, and we see that this has 0 Gibbs free energy of formation. So the Gibbs free energy of formation for the H plus in aqueous form is just 0. But if we look at the OH radical down here, it does not have a 0 Gibbs free energy. So the Gibbs free energy of formation of our OH minus radical, again, aqueous form, so dissolved into the water, is minus 157.24 kilojoules. And so if we go back here, our delta G of formation then, or our delta G for the reaction, is going to be the right-hand side minus the left-hand side. So our products, 0 for the hydrogen and minus 157.24 kilojoules for the OH, and then minus our reactant, in this case, of minus 237.13 kilojoules. And the difference between those two, the delta G of our reaction, is 79.9 kilojoules. And so if we look at our constant, then it's E to the minus 79,000 joules over 8.31 joules per Kelvin, and 298 kelvins. And that's going to give us 10 to the minus 14. So a very small number, 1 times 10 to the minus 14. So we could write then our equation here, that the product of the molarities of the hydrogen plus and OH minus molecules is 1 times 10 to the minus 14. But the number of H plus and OH minus radicals must obviously be the same, because we formed both of those by breaking up a single water molecule. And so the molality of H plus must equal the molality of OH minus, and these two combinations mean that each of those equals 1 times 10 to the minus 7. And this is where the concept of water having a pH of 7 comes from. pH is defined as minus the log base 10 of the molality of H plus ions. So in other words, if you have more H plus radicals in your water solution than pure water will naturally have, right? Pure water will naturally have this 10 to the minus 7 in there. But if you have more of those per kilogram of water, then your pH will be less than 7, and you've got an acid. And if there's less OH plus radicals, then your pH will be greater than 7, and we call that a base. Right, so acids and bases have to do with the number of hydrogen radicals floating around in your water solution. If it's less than water would naturally have, then you've got a base, and if it's more than water would naturally have, you got more protons in that water than you are in that solution than water does, then you're acidic. All right. Our next example will be oxygen dissolving into water, which as a chemical reaction we might represent as O2 in gas form going into O2 in aqueous form. And if we go look at the our table again here, O2 down here in gas form has a formation Gibbs free energy of 0, but O2 in aqueous form has a Gibbs free energy of 16.4, and so the change in the Gibbs free energy for the reaction, then the delta G naught is going to be 16.4 kilojoules. That's the aqueous minus gas form. That's for 1 mole of oxygen at 1 bar pressure in a kilogram of water, giving us a molality of 1 on this end. And so again, the equilibrium condition must be that the chemical potentials are equal. But on the left we have the chemical potential of oxygen in gas form, and on the right we have the chemical potential of oxygen as a solute. So the gas form, we can use the ideal gas law version we used for the nitrogen, and the solute we can use the the aqueous side we can use the solute from the dilute solution limit. And so the gas side, this gives us a mu naught gas plus the kT log of the partial pressure over P naught. And on the solute side, we have our mu naught for solute plus a kT log of the molality term. So again, this is the ideal gas chemical potential. This is the solute in a dilute solution chemical potential. And again, we're going to pull the kT log terms over to the left. So that's going to be kT, the logarithm here of P over P naught on the top, and molality on the bottom. And on the left, or on the right-hand side here, we're going to have the mu naught of the solute minus the mu naught of our gas form. As usual, we're going to again multiply by Avogadro's number across the board, and the thing on the right turns into an RT log of partial pressure over P naught divided by molality, and on the right-hand side we get Avogadro's number times the difference in chemical potentials, which is again our delta G naught. As usual, we can then pull the RT over, undo the logarithms, and we're left with, after some work, M divided by 1 over P over P naught is going to give us e to the minus delta G naught over RT. Again, a equilibrium constant K. And in this case, if we plug in our numbers, again, our delta G is 16,400 joules. So our equilibrium constant K, e to the minus 16,400 joules over 8.31 joules per Kelvin and 298 kelvins gives us a number something like 1 in 750. And again, once we know this constant, then we can make predictions for how changing, for instance, the ambient air pressure would change, or the ambient pressure of the oxygen would change the ratio of the amount of oxygen in aqueous solution to the amount of oxygen in gas form. And our final example that we're going to use or look at here today is the ionization of hydrogen. Again, the reaction here would be you have a hydrogen atom which can break up into a proton and an electron, or vice versa. Again, we're going to assume ideal gas forms for all of these. We're going to take hydrogen in gas phase, protons and electrons, free protons and free electrons, and so we're going to use the ideal gas solutions for those chemical potentials. Mu naught hydrogen plus kT log of the pressure of hydrogen over P naught equals mu naught of protons plus kT log of partial pressure of protons over reference pressure plus mu naught of electrons plus kT times the logarithm of the partial pressure of electrons relative to our reference pressure. And again, we're going to collect the KT terms on the left and the potential, or the chemical potentials on the right. And on the left, that's going to give us KT times the logarithm. On the top, we've got pH over P naught. And then on the bottom, we're going to have the PP over P naught times PE over P naught. And two of those P naughts are going to cancel. And on the right, we have mu naught P plus mu naught E minus mu naught H. So this left term here we can simplify slightly. KT logarithm of partial pressure of hydrogen, ambient pressure, reference pressure, and the partial pressure of protons and the partial pressure of electrons is equal to, again, this difference in the chemical potential of the products versus the chemical potential of our reactants. Now, in this case, for single particles like this, we can go right back to our ideal gas law descriptions for the chemical potential from section 3.5. We said that the chemical potential, again, that we derived using the Sacher-Tetrode equation, minus KT times the natural logarithm of V over N times 2 pi mass times KT over Planck's constant squared, and all of that to the 3/2. And we can use the ideal gas law to convert V over N into NKT. So V over N is equal to KT over pressure. So we can replace that with KT over pressure minus KT logarithm of KT over pressure times 2 pi mass KT, Planck's constant squared, all of this to the 3/2. So that's the chemical potential for each one of our chemical potentials. We can put a term in there that looks like this. Now, this formula was based on just the kinetic energy in our from our analysis back in chapter 3. But one other thing that we want to keep track of is the fact that the hydrogen atom here has not only the kinetic energy of hydrogen in motion, but also has the electrical potential energy, because there's a positive and a negative electron, or a positive proton and a negative electron sitting next to one another, and so there's some electrical potential energy, and we're going to include that electrical potential energy by basically including the ionization energy for hydrogen, which is 13.6 EV. We're going to include that ionization energy into the chemical potential for hydrogen, so that the chemical potential, the mu naught for hydrogen itself, is minus KT times the logarithm of KT over our reference pressure times 2 pi the mass of hydrogen times KT over Planck's constant squared to the 3/2, minus also the ionization energy term. Okay? And we can continue this for the other two chemical potentials, the chemical potentials or the unmixed chemical potentials for protons. That's this minus kT logarithm of kT over reference pressure times 2 pi mass of the proton, this time kT over Planck's constant squared to the 3/2. And for the electron, minus kT times the logarithm kT over reference pressure, 2 pi mass of the electron, kT over Planck's constant squared to the 3/2. So we can go back to our equation here and plug in these values here with these values here. Now notice that they have very similar forms, and in particular, if we look at this, there's going to be a chemical potential of a proton minus the chemical potential of the hydrogen atom, and the proton and the hydrogen atom are going to have very, very similar chemical potentials. So let's go ahead and just look at that part of it. Mu for the chemical potential for the proton minus the chemical potential for hydrogen, and that's going to be minus kT times the logarithm of kT over the reference pressure, 2 pi mass of the proton times kT over Planck's constant squared to the 3/2. But then we're going to have plus kT logarithm of kT over the reference pressure, 2 pi mass of the hydrogen atom, kT over h squared to the 3/2, and then plus this ionization term. And this is going to be the difference in a pair of logarithms here. We can see the difference here is a pair of logarithms, which means that we're going to take the things inside the logarithm and divide them one by one another, which means that these kT over p naughts are going to be able to cancel with each other. And in fact, everything here will cancel, except that we'll be left with an MP over an MH. And the mass of the proton versus the mass of the hydrogen atom, yes, they are very, very slightly different, but down by about 1 part in 1,000 or so. And so for the purposes of this exercise, we can make a very good approximation just by saying that the mass of the proton and the mass of the hydrogen are so close together that they're not going to make that much difference, certainly not compared to the ionization energy here. And so that leaves us with everything canceling except the ionization energy term. The difference between the chemical potential of the free proton and the chemical potential of the hydrogen atom is in fact just the ionization energy between the two of them, which means that this whole term over here on the left, the difference between all the chemical potentials, is just mu p minus mu h plus mu e. That's the ionization potential minus kT times the logarithm of kT over reference pressure, and the term for the electron to the 3/2. And if we divide everything through everything in this equation through by minus kT, that gives us a minus logarithm of pH p naught over pp and pe equals the logarithm of kT over reference pressure times 2 pi me kT over Planck's constant squared to the 3/2 minus the ionization divided by kT. This negative sign just gives us a flipped version of that, and so if we multiply if we undo the logarithms here, that will give us pressure of protons, pressure of electrons divided by pressure of hydrogen, and our reference pressure equals kT over our reference pressure times 2 pi mass of the electron kT over h squared to the 3/2 e to the minus I over kT. That's a minus I. And the partial or the reference pressures here cancel. And typically we write this equation as the ratio of protons to the ratio of hydrogens. In other words, the partial pressure of protons, the partial pressure of hydrogen. In other words, the ratio of ionized to unionized hydrogen atoms. That's going to be kT divided by the partial pressure of electrons, 2 pi times the mass of the electron, kT over h squared to the 3/2 times e to the minus ionization energy over kT. And this is a very famous result called the Saha equation, which gives us the equilibrium ionization ratio as a function of temperature for hydrogen gas. This equation is extremely useful in astrophysics of various types, stellar astrophysics in particular, but lots of astrophysics uses the Saha equation as an approximation, or at least as the equilibrium solution for the ionization. Hydrogen being by far the most abundant gas in the universe, you can see why the Saha equation would be quite useful in a lot of occasions. So there we have it. We have 4 examples of using the chemical equilibrium condition that the chemical potentials at equilibrium have to be equal to one another on both sides of the chemical equation, so that the chemical equilibrium of the chemical potential of the reactants and the chemical potential of the products have to be equal when we're in chemical equilibrium. And then we walked through 4 different examples, 4 different kinds of cases for how to work with those, and we'll do some homework problems, or some problems in the homework that we'll look at these and do some other examples. All right. Next time we're going to start in on our discussion of, we're going to go back to statistical mechanics version of things, and we're going to start in on a new topic there with Chapter 6.